Okay. Okay, so you all got my mail, right? That we'll have regular classes this week, and next Monday would be the midterm, first midterm. Okay, and the homework, the first homework that you did, we will try to return it by Thursday, and the second one, that's a programming assignment. Will take some more time. Okay, so what I'm hoping to do actually is sort of uh, complete the discussion of PalmDPs today, and then maybe there'll be some leftover. We'll talk about that on Wednesday, and then maybe review what we did once quickly, or take your questions, and so that we can have the midterm on Monday, and then we'll start new topic on Wednesday. Okay. Any questions before I start? Okay, so assuming that this thing works. Where am I? Okay. Yeah, so we looked at PalmDP model, right? And the idea, of course, is that we want to come up with a optimal policy which has to obviously take into account the evidence, that is the observations that are being seen, okay? And one of the questions before we go forward is actually useful to look at the computational complexity. It's a, as I mentioned, it's a terribly computationally hard problem. In particular, just as for MDPs, for PalmDPs too, you can talk about finite horizon or infinite horizon cases. Okay, so let's talk first about finite horizon. And those of you who completed looking at the textbook value iteration before coming to the class, was that for finite or infinite horizon? Finite horizon, right? So actually infinite horizon wasn't even described in the textbook. So the finite horizon, it turns out, is p-space hard if it is for finite horizon MDP, PalmDPs, it's p-space hard. Okay. So in contrast, what can we compare it to? We can compare it to MDPs, right? If you compare it to MDPs, in comparison, MDPs, finite horizon is basically polynomial in number of states. Okay, polynomial in the number of states versus now it became p-space hard. Okay, now the other interesting thing to know is that if suddenly you lose your eyesight, I mean, if you don't actually get observations anymore, you're unable to see any observations, okay, then it becomes NP complete. Okay, now, so MDP basically means full observability. If it's full observability, it's polynomial. Okay, if it has partial observability, it's p-space complete, p-space hard. And then if it is full unobservability, it's NP complete. So that means losing your eyesight is worse than having full eyesight. But apparently, it is better, computationally speaking, than having partial eyesight like me. Okay, that's the thing that we talked about before, as to where do you think the computational hardness will be higher. The computational hardness will be higher. Can somebody remind me of something analogous to this in some other dimension where the extremes are actually easier than the middle? Consider actions think of deterministic, one end, non-deterministic, the other end, that means I have no idea what happens, stochastic in the middle. Okay, so non-deterministic actions, planning with non-deterministic actions is harder than planning with deterministic actions. But it turns out to be, in some sense, easier than planning with stochastic actions. And we talked about this, right? We talked about this. This is the kind of thing I can ask on, midterm, basically hoping that people are hearing what I'm saying. And why does this happen? Why is it that it can be hard in the middle, in the stochastic case? I mean, in particular, how come this is actually easier?
Because you have, in a stochastic case, you have more knowledge compared to a non-deterministic case. So if you have knowledge, you have to make use of it. Whereas in the non-deterministic case, when you don't have knowledge, you can easily say that it can't be done.
Yeah. So that's on the right direction, but also in exactly why would I not use unobservable case? If I'm an agent, why would I not use unobservable case? Given that unobservable case, I mean, if you have partial eyesight, you can make it complete no eyesight, right? By just closing your eyes. Agents have that ability. Okay, clearly they can get a faster reasoning, a faster decision mechanism. NP-complete is the optimal policy. Why don't they try that?
You get better decision making.
Exactly. So that if you really don't have eyes, then basically, if you do have eyes and you close your eyes, then in essence you are getting lower, cumulative reward than you could have got if you used your eyesight. You see what I'm saying? But for the guy who doesn't have eyesight, then it doesn't make any difference because they will get the optimal that they can get without eyesight in NP-complete, computation. Okay, so that's something that is interesting to keep track of, so in some sense, taking into account, I mean, there are certain things about PalmDP that I hope you'll come through today's class, and hopefully it also came through from your readings. There are certain things that you need to think like a little bit more to realize that there are these sorts of interesting aspects that happen because you have, partial observability. One of the things that we talked about last time already is the only, in a belief state MDP, for example, which is what PalmDPs will become, the actions are what? In the MDP belief state, if you apply an action to a belief state, you get how many belief states? One. So it's a deterministic, transition in the space of belief states. The only choice comes, the only uncertainty comes in terms of what particular observation you get, right? Because the belief state itself says you have this probability of being in this state, this probability of being in this state, this probability of being in this state. And in the real world, you are in one of those states, actually. And that state, with some probability, gives out an observation. And it's this observation that you use to basically update your beliefs on the states. Okay. Anyway, in terms of the complexity, one is the finite horizon itself is quite bad. It's p-space hard versus NP-complete versus for unobservable versus polynomial in the number of states. Now here is, since when we were in MDPs, we were considering the fact that polynomial in number of states is not such a great thing, right? Why? Polynomial in the number of states. Yeah, understand. So number of states is not such a great thing. It is better than exponential in the number of states, right? But it is not such a great thing because you can have too many states. Because normally what you would like to think of is the number of state variables. Right? If you have v state variables, then you have 2 power v states. And MDP is polynomial in 2 power v. That means actually it's exponential in the number of state variables. You see what I'm saying? Now, one of the interesting things is, so the exponential in the number of state variables, number of states. Now, one of the interesting things is, so if you are using state variables, you're talking in terms of factored representations. Okay. In terms of the input, if you're considering input in terms of the number of state variables, the deterministic case itself, the deterministic planning with bounded length. That means if I give you an initial state and a goal start and a bunch of deterministic actions, and I'm asking you to find a sequence of steps that take you, optimal sequence of steps that take you from the initial state to the goal state, and I want the length of the plan to be only k or less. So that means I never have to go deeper than k in my search. Okay. It turns out for bounded length planning, it's NP complete. Bounded length deterministic planning is NP complete. Okay, so there's an NP complete here, and there's an NP complete here. But they're very different NP completes. Okay, because the complexity is always in the input size. This NP completeness result is when the input size is measured in terms of state variables. Okay, all deterministic planning is polynomial in the number of states. I mean, all deterministic planning of deterministic planning of size, bounded length deterministic planning is polynomial in the number of states. Okay. However, even for factored case, actually for bounded length planning, it turns out to be NP complete. Okay. And if you don't put a bound, that's sort of like infinite horizon, sort of an idea for deterministic planning, that would be p-space complete. Okay, I'm just bringing this up only. I'm here only to kind of contrast these to these results. These are at the states there, in terms of the atomic states, number of atomic states. And if you're already dead here, then you start thinking about factored input, then you'll be much worse, because you'll be exponentially worse in terms of the complexity. Okay, so that's the POMDP for finite horizon. For infinite horizon, things become more, can only become more interesting, right? And it turns out it's undecidable. That means finding optimal policy for an infinite horizon POMDP is an undecidable problem. Okay, and then, however, there are interesting approximation results, which we'll again not go into, but just to give you a feel for how hard things have gotten. Okay, for the approximation results, where if you are looking for a policy within epsilon of the optimal policy, okay, that part is NP hard. Okay, and similarly, bounded memory control problem. This is something we'll understand this better as we go on today. One of the interesting questions for POMDP winds up being, how do you store your policy? How do you store your policy? Okay, for MDPs, it's simple. You just get a nice little table. Okay, the table says S1, A1, S2, A2, S3, A3. Okay, for if you are in state SI, do AI. That's the policy. So the size of the table is what? S, the number of states. Now for POMDP, what will happen? POMDP, we convinced ourselves last week that you need to keep track of the history. Okay, and we also sort of, partially convinced ourselves last week, and we'll convince ourselves more completely today, that one way, basically history keeps increasing in size exponentially as the horizon keeps increasing. Okay, and so now you need a way of obviously sort of compactly representing the history. One way turns out to be thinking directly in terms of belief states. Okay, we'll jump to that, although I will have to establish that again today. Now, if I just say, so basically PALM DPs I mentioned last time are nothing but MDPs in the belief state space, in the space of belief states. So now optimal policy for PALM DP would be just a mapping from belief state to action. The problem is, how many belief states are there? Infinite number. You see what I'm saying? So the tricky part, so you might say, well, actually it's not that bad. The number of actions is finite. That still doesn't matter, right? Because, based on every specific belief state, you might wind up doing a different action. Multiple different belief states might wind up doing the same action, but if they are not in some contiguous region, then you still need to represent them. So if you have a very crinkly process where if this is belief state B, then you do A, and then you change the distribution like just little, epsilon power minus 1000, epsilon power 1000, okay, and it will change the action. That could happen in theory. In theory, that could happen. So just representing the policy, optimal policy for PALM DPs is an issue that you need to deal with. This is not as much of a problem for finite horizon PALM DPs. That's why you looked at finite horizon PALM DPs in the textbook, right? Because in finite horizon PALM DPs, in essence, as you saw there, you just tend to think in terms of conditional plans of depth k, where k is the finite horizon. Okay. So anyway, it basically, the point is that because you have the policy can just become unboundedly large. Just the representation of the policy itself can become unboundedly large. No physical agent really can represent such a policy. Okay, so you might then say, well, I have 5 megabytes to represent my policy. Find me the best policy among all 5 megabyte policies. You understand what I'm saying? Which is not a question you ever asked in the context of MDPs. In the case of MDPs, you never cared about, there is no additional memory problem other than just the size of the MDP. If you could represent the size of the MDP, then you could represent its policy too. However, in PALM DPs, you may have enough memory to represent the PALM DP, but you still have zero chance of representing the full policy. And so you might wind up bounding the memory and then say, find me the best policy that can be represented in a bounded memory. Okay, and that's a very interesting problem that we have to think in the context of PALM DPs, and that turns out to be NP. That's a kind of an approximation algorithm, and again, it's an approximation that is sort of desperately needed, because otherwise, how are you going to represent the policy? Okay, so that's about the complexity of PALM DPs. Okay. Now let's go forward. So we did this. This is basically your representation of PALM DPs. There again, this is a useful thing to know. I just mentioned it just now. So for PALM DPs, you know that MDPs already have this notion of curse of dimensionality, which is just the number of states. As the number of states increases, there's basically the size of the state space increases. MDPs are becoming harder and harder to solve. Okay, but for PALM DPs, you also have the curse of memory. Okay, that means you need to see basically the size of the value function, are equivalently the size of the policy. So here's the interesting thing. So size of the value function basically is the value function is not going to be in terms of the states. It has to be in terms of belief states, right? Okay. Now there are infinite number of belief states. The only hope for PALM DPs to be tractable is that for regions of belief states, for contiguous regions of belief states, the value behaves in a regular way. In particular, what you saw was, this piecewise linearness of value function. Okay, because of which you'd essentially see in the value iteration that you saw, essentially you are taking the upper envelope of a whole bunch of value functions corresponding to different conditional plan alternatives. Okay. So now, in the case of infinite horizon MDPs, it is actually possible. So you saw these kinds of pictures, right? I'll see them in a minute too. But you saw these kinds of pictures. Okay, and if you have that, then the value function that you can basically consider is that. What did I do? Okay. Yeah. Where are we? Okay. I'm sorry. I don't know why this is happening. Oh, we have two of these for some reason. It'll be fine, believe me. One of these days. Okay. Okay. So what I was saying is that, basically for finite horizon case, you could be sure that the value function can be represented. Value function can be represented in this piecewise linear fashion, which essentially means, remember again, value function also can be infinitely large, just as a policy function can be infinitely large, value function can be infinitely large. The size of the function depends on how many x values are there. Okay, the only difference between the policy and value is the y value, essentially. Okay. So for finite horizon, you are in good shape. For infinite horizon, actually, the value function may not even be representable in finite memory. Okay. So there is this issue of curse of dimensionality as well as curse of memory, and the curse of memory is something that you have to worry about only for POM-DPs, because we never had to deal with it for MDPs, because you essentially had the full state in front of you. And in fact, you will see this, you probably saw this, I mean, you should have seen this if you read the textbook, that the number of the conditional plans that you have to consider, for example, increases essentially in an exponential way, when you go from k depth to k plus 1 depth. Because you have to then compare all these conditional plans and see which is the best. So the per iteration complexity of the dynamic programming itself exponential. See what I'm saying? You saw this, so I can again mention it here, but we haven't actually come in the discussion here itself to that point. Okay. So the policies can be represented, basically policies have to be represented in some compact way, partly because your policy is mapping history to action. The history can grow unboundedly as the horizon increases. Okay. So there are two ways to summarize history. So we say formally one is belief state, where you just keep the distribution over states. The current distribution over your states. Given all the information, what's your current belief distribution over your states? The other, it turns out, is kind of represent the policy itself as a sort of basically take the history which is growing unboundedly, split it into, partition into just k equivalence classes, and then say if you are in this equivalence class, you will have one particular action. So this is sort of memory bounded policy representation. Okay, there are lots of interesting algorithms for POM-DPs which essentially represent the policies in this form, in this way, but we won't look at it in our class. We'll mostly just look at belief state based representation. Okay, and we'll just look at the finite horizon version of it. That's the only thing we'll do. Okay, so what is a belief state? As I mentioned, and it's probably not too surprising to you, belief state is nothing but a probability distribution over states. So geometrically, you can think of belief state as a simplex in k dimensions. If you have k states, then there is a k-dimensional simplex which is the plane of all the points whose coordinates are all positive and they add up to 1. That's the simplex. That's the definition of a simplex. Okay? And if they add up to 1, they also can be given the semantics of a probability distribution. Right? So basically in 2 dimensions, a simplex looks something like this. Right? Essentially, this is the set of all points where the probability, the S1 plus S2 values, S1 plus S2 equal to 1. This is the line S1 plus S2 equal to 1. That's a line. Okay. And then similarly, in a 3-dimensional case, a simplex looks like that. In 4 dimensions, of course, I can't draw a picture, but it's worth thinking in terms of these simplexes. And the advantage of these simplexes, thinking about this, is now you know that even though there are only 2 states, the states in MD, the states and the underlying states become the dimensions, okay, for the POM-DP. And then the actual states, the belief states, would be points on the simplex. And so even if you have just 2 dimensions, you have infinite number of belief states. Right? Okay? And so, by the way, this simplex will come of use and one more time, at least in this class. I mean, of course, you haven't thought about it before. I mean, I know some of you have probably thought about simplexes in various places. But when we talk about LDA, once again, we will look at simplexes, because that's a useful thing there too. But anyway, so you have belief states, and if you think in terms of belief states, the nice thing is the process of maintaining your belief state is Markovian. process of maintaining your belief state is Markovian. Okay, that means given the current belief state, the next belief, and you do an action A, then the next belief state only depends on the current belief state, not on how you got there. That's why history goes away. Okay, and so for any belief state, the successor belief state depends only on the action and the observation. And then this we discussed. Why doesn't observed state itself have Markovian property? That's like the blind spot example we discussed. Okay. We talked about this last time already, but by the way, notice in doing this, after moving left 5 times, after moving up 5 times, after moving right 5 times, okay, what happened to the observations? In a PAM-DP, as soon as it moves, it gets an observation. So in this particular case, we decided to ignore the observations. That's the thing. The good thing about having eyes is you can decide not to use them. If you don't have eyes, then you have no choice of using or not using. You only can't use them because you don't have eyes. But if you have eyes, you can close them, right? So in this particular case, what I have shown is anytime I tell you a plan of that's sequential, that means you don't care about what's happening in the world. You see what I'm saying? I'll do this and then I'll do this and I'll do this and I'll do this. Then I'll ask, after doing the first one, what do you know? What has happened to the world? You don't care. And it can happen in 2 different ways. You started from a complete state and you did a deterministic action, so you know what the next state is going to be, so you are sure what the next state is going to be. Why waste time checking? The other is you have no sensors. Are you too lazy to actually look? In which case you are going from a belief state to belief state, okay, and you are ignoring the observations. You see what I'm saying? Okay, so that's this example basically is not a PAM-DP example. This is a norm-DP. In this particular case, the action here was being done without looking at the observations. A policy which basically says left, 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 or right, 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 or right, left, right, left, right, left. They're all non-DP policies because they ignore the observation. Any policy that takes into account observation has to say left. If observation O1, then do right. If observation O2, then do left. Okay, the moment you do this, you get a tree structure for the plan. Not a line structure, but a tree structure. And that's kind of the complexity of PAM-DPs, because there are many more trees of a given depth than lines of a given depth. Line plans, sequential plans of a given depth. Okay? But you need to learn to appreciate the fact that you have so many more choices, because then you can use these observations to reach higher value. Okay? Okay. So now finally let's talk about acting in a PAM-DP. So let's assume that you start in a belief state B. What is a belief state B? You assume that belief state B is such that it takes S and gives it a value, a probability. Okay? So B of S is the probability that the agent thinks it is in state S. Okay, so B is a distribution. Okay, so it currently is in a particular belief state which is giving specific probabilities to all the states. And then the agent decides to do an action A. Okay, presumably because its policy said that whenever you are in belief state B, you must do action A. That's your optimal thing to do. Okay, now that's where the question is, how do you represent the policy phi of B? if you are representing it directly as a big table of belief state 1, this is the action, belief state 2, this is the action, you're dead. Right? Because there are infinite number of belief states. And the way finite horizon of POM-DP actually avoided that problem is it represents it in terms of basically conditional plans that you will start from this state. Okay, and they would be a finite depth because you're only doing k depth action. Okay. Anyway, so you do an action A given by policy pi B. I mean, it doesn't really matter why you did this action A. Okay, when you're acting, you just decided to do a particular action A. Now, question, of course, is having done the action A, you want to, in your own mind, the agent in its own mind can compute what the next belief state is going to be. Compute what the next belief state is going to be. Okay, and this is basically, so it projects. So suppose if action A basically says, if you are in S1, I will take you to S2 with 0.5 and S1 with 0.5. Okay, and then if you are basically what you are doing is you are actually applying this action to your belief state to compute the new belief state. You've done this in the context of non-deterministic case. Now you can also do this in the context of just computing the new belief state directly. Okay, and all this new belief state is saying is the probability. So for the new belief state B dash, I need to compute what is the probability that I am going to be in a particular state S. Okay, after doing this action A. Okay, and that would be after doing action A, I was originally, so again, remember that I was in actions in a particular state S, I did an action A, then the probability that I would be in S dash is given by the action's own description. Now, of course, I'm not sure that I'm in state S, right? The probability that I'm in state S is given by B of S. Okay, now notice that I may have gotten to S dash either by doing A in S or doing A in some other state. Multiple different states, doing action in multiple different states might just still get me back to S dash. So I have to sum over all possible states S, such that, the probability that I currently am in that state is B of S times the probability that if I did the action A in that state, I will get to S dash. If you sum this, that will give me the probability I am in state S dash. Right? So this is B dash of S dash. Okay, that's a new representation, that's a new belief state now. Okay. Okay. So at this point, you have done all you can in terms of thinking about how the world works. Because you have your current understanding of where you are is completely given by B of S. And your current understanding of what actions do is being used on B of S to compute where you would be after doing that action. There is still a lot of uncertainty left. Because B dash of S, the new belief state B dash is still a distribution. It's not, for a belief state not to have any uncertainty, it has to be an impulse function, basically. It should put all its probability in one place. Right? Okay, so this is where you will stop if you have noise. But if you have eyes and if you have sensors, then having done this action, this is where you stop, either if you have no eyes or you have no interest in using them. Okay, but if after this, you then essentially, if you do have sensors and you want to use the sensors, you get the observation, now that you did this action in the real world, remember, this is acting in the PALM-DB. First, you need to understand acting in the PALM-DB before you can understand how to come up with the policy. Okay, we didn't make a huge deal about acting in the MDB. Why? Because it's not that complicated, essentially, right? Basically, you know exactly which state you are in. The policy tells you what action you are supposed to do. You do the action. And then you know which state you got into. And then you look into the policy. And so I can write like a slide like this, but it's a much smaller slide. In the case of PALM-DB, it's actually a much more interesting scenario. Okay, even acting is non-trivial. That's the interesting part to understand. This is why actually I mentioned that this idea of filtering, it's about to come right now. Filtering is changing your beliefs in light of observations. Okay, before you opened your eyes, notice that this step and this step sort of occur instantaneously, right? I mean, it's like in the real world, you do an action, if these actions are instantaneous, as soon as you did the action, you got the observation. Okay, however, your thinking can be split into two parts. Your processing can be split into two parts. In the first part, you thought, okay, I'm about to do this action, so what do I expect after doing this action? I expect B dash. You see what I'm saying? Now, I did this action, and I got an observation E. The question then is, should I still assume that my belief state is B dash, or should I assume something else? So, in particular, think about the following scenario. Suppose it so happened that I came up with, suppose I only have two states, S1 and S2. Suppose my observation model is somehow such that S1 is the only one which will give observation O1. S2 is the only one which will give observation O2. That's possible. It's a specialized PALM-DB, but it's still PALM-DB. So in fact, it's MDP in this particular case, right? So now my B dash of S maybe, let's say, is 0.5, 0.5. Or maybe even, I don't know, I can change that. I can say 0.7, 0.3. That is, after having done my actions, I've decided that I must be in state S1 with 0.7 probability, state S2 with 0.3 probability. Now I got O2 as my observation. What is my belief state? S2. That's it. Right? Right? You can't just say, I'm assuming still it's 0.7, 0.3. In this particular case, the moment you got the observation, okay, obviously, in this case, the moment you got the observation O2, this is just wiped out. Okay. Now, of course, this observation model has the property that this actually becomes fully observable. In some sense, the observation names are equivalent to the state names. That is why in MDPs you don't do these two steps, because one of them, everything else except the reality will just get wiped out after the observation. Okay, but on the other hand, if I make this model a little more interesting, suppose I said S1 gives O1 with 0.1 probability and O2 with 0.9 probability. Okay, and S2 gives O2 with S2 gives, I'm sorry, okay, let me change it since I want to stick to the same example. So S1 gives O1 with 0.9 probability, O2 with 0.1 probability, S2 gives O2 with 0.9 probability and O1 with 0.1 probability. Right? So in fact, either of them can give either of the observations. So it's no longer fully observable. However, in the beginning you thought you were in S1 with 0.7 probability, S2 with 0.3 probability. But having realized that you got the observation O2, you obviously must update your beliefs such that you are more likely to be in S2 than you thought you were. Right? Okay. Now that update has to be done. Sorry. Okay, that update has to be done. Now, how do we do that update? What? Yeah, but that update essentially is the classic update we always do when that's a Bayesian update. Okay, so basically you are, you have a prior probability, let's say. I want you to think in these terms so that things become much easier to see. So suppose you have a prior probability of disease. So as the patient walked into your office, you thought, prior probability of disease, suppose there are only 2 diseases, flu and malaria, okay? Those are the only 2 diseases. So you thought, 0.5, 0.5. That's your prior probabilities of the diseases. And the patient came in and is exhibiting symptoms of runny nose. Okay, now my question is, what is the disease probabilities given these symptoms? That, Mr. Bayes says, Reverend Bayes says, is Rn given D times PD by PRN. Right, that's what Bayes said. Now, this is disease causing symptoms. For us, the equivalent question we will be asking is, originally the diseases are our states. So we add a P of S, that's probability that you are in particular states. Okay, now you got P of S given E, that's what you need to compute. You got some evidence. Given that evidence, you have to recompute the probability over the states. That would be P of E given S times P of S by P of E. Evidence is symptom. State is disease. And you just did the Bayes rule to update the probability distribution. And one of the things you know from the Bayes rule thing is that, of course, this is given as part of your sensor model. This is called the sensor model. To describe an MDP, all you need to do is, what's the probability that when you do action A in state S, you'll get to state S dash. To describe a COMDP, you need to do that, plus you need to give me this. What's the probability that you'll get evidence E in state S? For every state S and evidence E combination. So this is part of the input. You have this. Right? And then this is what you currently were thinking, the prior probability of being in this state. That is what you got up until here. Right? Now the only thing that you need is the probability of evidence. Now there's a usual trick in the Bayes rewrite where you say that, that if, let's say, if you only have 2 states, you can compute PS1 given E and PS2 given E, that will be another formula. And both of them would be in terms of this P of E. I'll call 1 by P of E, I'll call it alpha. So it's alpha times this and alpha times another formula, another number. Okay, so at the end I'll get, let's say, alpha times 0.7, alpha times 0.3. Okay, now this has to be added to 1. Right, because S1 given E and S2 given E must add up to 1 because there are only 2 states, because of which you will get alpha back. Right, so that's the alpha there. I'm just reminding you, most of you probably know this, hopefully. Okay, that's where the alpha comes from. You see what I'm saying? So you just say, you can normalize the evidence out. Okay, so that's it. So here you had a B dash S dash, and the B double dash S dash. I mean, of course, I call it B dash S dash. So now I should call it something else. But let's say, so the new belief state is alpha times P E given S dash times P of S dash. Now P of S dash is this whole thing. You got that? You should try this out. To make sure that you understand this. For those of you who have done Bayesian calculations, this should be pretty obvious. But those of you who don't, you really need to do this. A couple of examples to make sure you understand. What you did just here, this is called filtering. You filtered your belief through the observations to come up with new beliefs. Yes?
If you have multiple action and then one observation.
Then you have to do this one after other. Oh, so you're saying, no, okay. Go ahead, what are you saying?
I assume you have 5 action and then one observation.
That basically is a complex scenario that you need to derive from this.
What I'm asking is that I have to do 4 steps.
Yeah, exactly. So basically you get, so if you ignore all the observations until the last action, then in essence you do this 4 times, then do the filtering. But you have to realize that you lost useful information by doing this. It's like, did you people play this game? Normally we walk while seeing. Once in a while you say, yeah, no, I feel like doing this, especially in orange wall when people are walking around. I'll close my eyes and take 8 steps and see again. Right? You see what I'm saying? It is not, not particularly optimal, especially with people slapping you because you're running into them. Okay? Which you would have avoided. Because you ignored, basically you took 8 steps, whatever steps you wanted, without seeing the evidence. And then of course, then basically 8 steps and you see somebody, you look staring right into somebody's face. Oops, okay, I'm kind of in the wrong action space now. I'll change my now. But you could have avoided even being here. You could have done much more optimal action. But it's a good question. The thing that you want to understand is taking evidence into account is always the right thing to do from the point of view of increasing your return. But it is intellectual laziness will stop you from taking evidence into account. That's exactly the reason why once in a while you like to close your eyes. Or once in a while you want to text while you're driving. Because then you are not looking at the rest of the world. You're sensing something else. Okay? And it will guarantee that you would not be optimal that way. Would you survive to see another day? You might. Okay? So that's acting in PalmDPs. Okay, so you should be able to do this. This is simple. This is comparatively simple. And in fact, the only interesting thing that you did here is this. This is the Bayesian update. Okay, now, if I know how to act, it turns out, so this is my controller for belief state. This is basically called a belief state controller. This is a PalmDP controller. So it assumes essentially that there is a policy phi which takes belief state B and spits out an action A. You don't necessarily ask right now how is this policy phi represented. It just takes the belief state B and tells you what action to do. Okay? And then the question, of course, you do the action A, at which point you get an evidence E. Now notice the way this picture is written. As soon as you did the action A, you can essentially compute your expected belief state, expected belief state. But then you also got this observation E, so you sort of de-normalize to take into account this evidence that has been presented to you. So what you essentially then will compute is PB dash given BAE. So what's the probability of belief state that you will be in belief state B dash given that you were in belief state B and did action A and got observation E. Okay? Based on that, you essentially now know what your B dash is. Now the interesting thing is a single B dash is split out here. Right? A single B dash is split out here because that's what we just did. We did this right now. We did an action in belief state B, we did action A, and then we got observation E, and then we computed B dash. there is no choice. There is no randomness. All the randomness is put into your belief state. Okay, and then now you got belief state B dash. So essentially, you keep that as your current belief state, and then look to do what next action. Okay. Now the question, of course, is who comes up with. I mean, first of all, you have to understand that this is the filtering part. This is non-trivial in itself, you know. But then you also want to think of how to come up with this policy. Okay. And the other thing is the way this picture is written, you have to take into account the fact that you, as the free agent, you have complete freedom to ignore E. Heck, you actually have complete freedom to ignore A. You can ignore everything. You do action A and then just think of another action and do that. Nobody can stop you. All we can show you is that mathematically, it's you are not guaranteed to be optimal. You may just luck out to be optimal in some particular case, but you are not guaranteed to be optimal if you ignore evidence, if you ignore the action model. Okay, so that's what we can say. What? Because I mean, we are taking the current belief state. Remember, in computing, the thing that this computation. If you remember, this is the final computation. This is the B dash. This one is giving you P of B dash given BAE. But that involved taking into account the original B. There are three belief states. The belief state, the first belief state where you are in, the belief state projected where you think you would be in without having seen any evidence, the belief state that takes into the evidence into account. That's why I started with B dash and B double dash. Okay, but in computing this guy, you need the original belief state because that's been taken here. That's why you have B going back here. Right? Okay, so yes. What? No, I did not. I said somebody computed the policy and gave it to me. This is all about action. Okay. This is all about action. But again, for other people from robotics here? Somebody in robotics? Yeah. So robotics people essentially assume somebody came up with the policy, and just executing the policy is non-trivial. Okay? They think it's hard enough. If you tell me what to do, it's still hard enough to figure out where I am while doing what I'm supposed to be doing. And the planning people think, how come you guys ignore planning? Well, we are ignoring planning because without doing planning itself, we can do something, our life is quite non-trivial. Okay? This is without even, this is assuming that there is a handwritten policy. Okay? But now I want to compute a policy that is optimal. Now the interesting thing here is this. If I give you the handwritten policy, so here's the interesting thing. So suppose somebody were to give you the optimal policy. In what way can you screw up here? Because you are not computing the policy. So you cannot be held responsible for being inoptimal because the policy given is inoptimal. You understand what I'm saying? Okay? So you have to always ask yourself, what things can be blamed on me? Right? If somebody is giving you pi, they can't blame you for the pi being inoptimal. But you can still screw up by not updating your belief state correctly. Do you see what I'm saying? So that's basically the non-trivial thing. Okay, just as like a as a throw off references. In general, this computation looks very easy, right? This computation looks very easy, but essentially the entire filtering community is doing this computation efficiently. you have to ask yourself is, suppose your state space is continuous. I'm making a little digression, and it's worthwhile doing it, especially since I did this 1 over x guy and some other people. Have anybody heard X filtering? I said filtering. Have anybody heard what is it?
Particle filters.
Okay. And what else?
Kalman filters.
Kalman filters. How are they connected? I'm talking about filtering. Why does Kalman become famous? Why do we need to come up with particle filtering? It's a very interesting point to understand. Here's the deal. We are essentially computing belief state distributions. We are computing them over discrete state spaces. There are only n states. So, obviously, if the original belief state distribution required s in n numbers because there are n probabilities, the new one will still require n numbers. The new one after that will still require n numbers. The new one after that will still require n numbers. We don't care about it. Imagine you have continuous states. How do you represent continuous state distributions? So when you have discrete state distributions, you still can, you basically assume that, oh, I can always represent the distribution extensionally, like in a little table. Of course, there are parameterized discrete state distributions. Can somebody name one? What? Poisson distribution is a parameterized belief state distribution, for example. Okay, so it's like curve fitting essentially. Okay, now if you have discrete states, then you have the option of only representing things in extensional form. If you have continuous states, you do not have the option. You just do not have the option of representing the belief states in a tabular form. So, people who do continuous state probability distributions never first think in terms of like little tables of probabilities. They start with parameterized distributions. Give me some famous parameterized distributions for continuous variables. Gaussians. Okay, I'm going to talk lots and lots of exponential family distributions. Okay, lots and lots of them. Now, one of the interesting things is, suppose I were to tell you that my original belief state distribution is some parameterized distribution P, which takes some, let's say, couple of parameters, maybe mu and sigma. Can take more, as long as it's not as many as, as long as it's not infinite number of parameters, we are happy. Okay. Suppose I started with a nice, happy, 2-parameter distribution that exactly represents where I think I am. I do an action A. I compute my B dash. Okay, which involves essentially computing the projected B followed by the filtered B. Okay, so suppose I started with a nice distribution like that, and it has mu and sigma. Okay, and then after B dash, I got a distribution which is like this. Now it's no longer in the same family as the original distribution. It requires more parameters potentially. In the worst case, your new distribution can be so arbitrarily crinkly that it can require infinite number of parameters to represent. Come Rudolf Kalman, who pointed out that, look, we are all anyway crazy enough to assume that everything is Gaussian. So suppose you were to assume that the belief state is Gaussian. Suppose you are also to assume that the observation model is Gaussian. Then I can show it to you that the new belief state that you get here would also be a Gaussian. It will just have different parameters. The thing is not how complicated those two parameters are, but that there are exactly two parameters. I mean, if it's a two-dimensional Gaussian, it's a one-dimensional Gaussian, there's two parameters. The number of parameters doesn't increase. That's the great thing about Kalman filters. Okay. Now, what did Kalman filters do? It just assumed that the initial belief state is Gaussian and the observation model is Gaussian. Are they always Gaussian? No, of course not. If not, what do? You try to do things like extended Kalman filtering, where you say it's a mixture of Gaussians, and then I will take this mixture of Gaussian into another set of mixture of Gaussians. At some point of time, this whole thing breaks down. So that's where comes the particle filters. Particle filter says, well, let me represent the distribution in essentially in terms of k samples of the distribution. Now the tricky part is, how do I get k samples of a distribution? Now, you have to be careful. If I only have k samples of a distribution, suppose I have a distribution like this, k samples, it doesn't matter, no, I can take k samples like this. If I have a distribution like this, and I took k samples, I'll miss this. All the interesting stuff is going on here, I'll miss that. Okay? If you are not careful, all your samples will be stuck in the uninteresting regions. Okay? What particle filters wind up doing is to rearrange the samples such that you essentially track the areas where you are likely to have high probability. That's the connection between this little equation and the entire area of filtering. Kalman filtering or simple. Kalman filtering and particle. We don't have to thankfully do it because we are blithely assuming as of now that the states are discrete. Assuming that the states are discrete. We have given up to the fact that belief states are not discrete. Belief states are continuous. But the states are still discrete. But in many cases, states themselves are continuous. And that's where signal processing people have been doing this for. Okay. Now, so what I want to do is the last thing today, and then hopefully we'll discuss the value iteration under next class, I guess, a little bit, is that since you know how to act in the POMDP, I want to just write in some sense you can see that essentially if you think of this POMDP as an MDP in the belief states, which is basically what you see from this picture, really if you just, what's happening is you're going from B to B dash directly. When you do A and B. When you do action A, you're going from, and then get an observation E, you're getting into A. So, can I write down POMDP directly as an MDP in the belief space, which is what I've been telling you before. I just want to write down the formulas. Okay? And those formulas will make lots of sense given that we have done this already. All you need to do, think about this point. Here, up until here, you did not see the execution. Right? Up to that point, you only did the action A, and you're thinking in your head what the next belief state is going to be. This is where the execution happens. Suppose I don't want to do the execution still. In planning, I can't do execution. I have to think about doing execution, not do it. All I have to consider is, at this particular point, I can get any of the observations that are possible. Suppose there are k possible observations that could happen. Then in essence, I have to consider what if E1 occurs, what if E2 occurs, what if E3 occurs, what if Ek occurs. Okay? In fact, before I even go through the belief state one, let me skip over and then go here. In fact, just directly given your execution model, you can draw this picture. Okay? What this picture is saying is, this is your belief state. Okay? This is your belief state. And you could do an action A. Okay? As soon as you, in fact, that picture actually is slightly, really what that picture should look like is like this. You do a belief state. From that belief state, you can consider doing an action A. You will get another belief state directly in your head. But based on that belief state, you can get multiple possible evidences. Okay, E1 to Ek. You see what I'm saying? Okay, E1 to Ek. And for each of those, I will get a new normalized belief state. And I know how to compute this, essentially, just for any specific action and evidence combination, I can compute that belief state. I can compute that belief state using this. That's what happened. In this case, it actually happened. In that picture, you are imagining it happening. The interesting thing is, you drew pictures like this for MDP. The MDP version of this picture will look like this. I have a triangle, I do an action A, and I can get, for the action A itself, I can get state S1 or state S2 or state S3. Right? Here, when I did action A, I only get one belief state. I still have branching because I don't know which evidence I will get. You understand what I'm saying? So technically, it's quite interesting. I mean, if you think about it intuitively, it makes sense. Basically, evidence is playing the role of state. Okay. However, after the action, you know a unique belief state, which then gets denormalized based on the evidence you get. Now, the interesting thing is, based on just that slide I have shown you, you can draw this search space. For every action that I can do, and for every evidence I can get for that action, I can draw a branch and compute the left state for it. And under each of those belief states, for every action I can do, every evidence I can get, draw branches. Keep doing this, let's say up to level K. At the level K, I have belief states. This looks like, I would say, a min-max game tree taken to fix that. So what do we do normally? Give some approximate valuations to these belief states, these game positions in min-max. Here I can give approximate valuations to these belief states. We can figure out how to do it. Maybe you have some heuristic. Once you throw that in, then the advantage is, since this is chance node, what you get here is the average, or the expected value, backing up, while you are backing up. And under every triangle, what you take in is the max value. Because you pick the action that will give you the maximum backed up value. Do you see what I'm saying? Expect max, expect max, expect max. You do this, you would then see which action and which action branch is giving you the best backed up value. Do that. So after having made a huge deal about POMDPs being very hard to solve, this isn't that bad. I mean, if you don't care about being optimal, and you want to do POMDPs the way game trees are solved, this is what you do. In fact, if you just understood that one slide, you can do this. Because that one slide is being used to compute, essentially, given an action and evidence combination, what is the new the belief state. Right, that's what is happening here. So from this belief state, I can do any of these actions. Under each action, I can get different kinds of belief state, different kinds of evidences. After doing the action and evidence, I compute the new belief state. Right, and that's exactly what I was told. So the only thing that's left over is to actually see that what's going on here is a direct, MDP in the belief space. And to do that, I need to specify a normal MDP. What do I need? I need an belief state to belief state in terms of actions map. Okay, I need this PB dash given B and A. Now the tricky part is PB dash given B and A is not yet known right now for you, because you have seen PB dash given B, A, and E. condition it over E. So you remove that conditioning here by summing over all possible evidences. Then you get B dash given B and A. And then the reward for a belief state is nothing but the expected, basically the summation, the expected value of the rewards of the individual states. If you do that, this is your new transition functions for belief states, and this is your new reward function, and you have an MD. And it's fully observable, because you always know what your new belief state is. You see what I'm saying? Okay. So, and then you can actually do Bellman, based dynamic backtracking. Theoretically, everything is happy and sound, except there I put a sigma over B dash. That's a big laugh, because sigma is our discrete quantities. B dash is basically, you're talking about all belief states. The continuous quantities, it should really be an integral. Okay. And having shown the Bellman equation, next time what we will do is we just basically solve the finite horizon MDP directly in terms of the conditional plans of the horizon depth. Okay. One thing I want you to understand is make sure that you understand these two things. How B dash given BA is computed, which is in terms of B dash given BAE. This part you know from the previous slide. The only thing left is E given BA, evidence given B and A. And evidence given B and A can again be computed using normal rules of probability. Okay, make sure that you understand this. And eventually, evidence given B and A will get shifted into observation model, E given S dash. This is something that you can read off. And this is something you can read off. And this is something that you have. So I'm able to compute this with this, and this one I've already computed once. Make sure you understand.